Welcome to Unit 4 in the first module of the course. This is an important unit because up until now we've treated the virtual machine as an abstraction, and from now on we are going to actually build it. So to begin with, let's take another look at the VM abstraction. And basically I'm repeating the quiz that I gave you in the last unit. And in this quiz we started with some arbitrary stack machine state, and the question was which VM commands will implement the abstract operation static2 equals argument 1, leading to this final stack machine state. So you saw the answer, and the point that I'd like to make now is that everything that you see here is completely imaginary. It does not exist for real. And if we want to actually execute this scenario in some concrete way, we have to realize it on some von Neumann machine. So what do we have to do? Let's think about it. If you had to do it, how would you go about it? Well, first of all, you have to take these 4 memory segments, or actually we have 8 of them, and we have to somehow map these memory segments on the single RAM that is available for us. And to do it in some sensible way, right? We have to remember where each segment starts on the RAM and manage these locations and so on. And once we come up with this mapping, we have to do something with the commands, with the push and pop commands. We have to translate them into a sequence of machine-level instructions that will operate on this world that we just built on the RAM. So we have a lot of work ahead of us, but as usual, we'll do things one step at a time, and each step will be relatively simple and well-defined. All right, so in order to carry out the implementation of the abstraction, I'm going to use a technique known as pointer manipulation, which some of you may be aware of, and for some it may be new material. So I'd like to give you a crash course in pointer manipulation, and this crash course is going to last exactly 1 slide, so bear with me. Let us assume that we have a typical RAM, and we decided to use the symbols P and Q to refer symbolically to the first 2 RAM locations, RAM0 and RAM1. Now consider the following pseudo-assembly statement. D equals asterisk P to the and we decided to use the symbols P and Q to refer symbolically to the first 2 RAM locations, RAM0 and RAM1. Now consider the following pseudo-assembly statement. D equals asterisk P. What do we do here? Well, here's the rule of the game. Asterisk P refers to the memory location that P points at. So the asterisk notation tells us that we want to treat P as a pointer. Now, if we didn't put the asterisk, if we just said D equals P, then presumably we'll get the value 257, because that's what P points at. P is equivalent to 0, so D equals P will give us the contents of RAM0, and yet we said D asterisk P. So when we say D asterisk P, we imply an indirect addressing operation. So we look at the value of RAM0, which happens to be 257, and we treat it as an address. Next, we look at the value of RAM at this address, which happens to be 23, and we store it into the D container. So D becomes 23. So this is the gist of indirect addressing. Now, if we have to implement this thing in, let's say, heck, then here are the 3 statements that will make it happen. We start with at P, and by doing this, it's essentially the same as at 0, because P and 0 are the same thing in our assumption here. And then we say A equals M. This will cause A to become the contents of the selected memory register, which is register number 0, and therefore A will now contain 257. Now remember that A is an address register. So once we put a certain value into A, like 257, automatically we're going to select register number 257 from the RAM. So this will become the selected register, which in the hack assembly language is represented by the letter M. And therefore, when we next say D equals M, we're going to get the value of this register, the currently selected register, number 257, and the value happens to be 23. Now, everything that we did here is quite similar to what we did in Project Zero of this course. And if you did Project Zero, you shouldn't be surprised by what I just described. If you didn't do Project Zero, then I strongly suggest that you stop the video, take about an hour or two of time and do Project Zero. Submit it, and only after you understand how to use the hack assembly language will you be able to follow the next modules and really do them effectively. So assuming that you've done that and you understand the hack assembly language, let's move on to the next example. Now, what is the meaning of to follow the next modules and really do them effectively? So assuming that you've done that and you understand the hack assembly language, let's move on to the next example. What is the meaning of P minus minus and then D equals asterisk P? Well, X minus minus is shorthand for X equals X minus 1, or sort of a decrement operation, and X plus plus is the same with increment operation. So if we do P minus minus, well, we now treat P as a regular variable, and therefore RAM 0 will become 256. And now P points at address 256. So if we say D equals asterisk P, we'll get the value 19, which happens to be the contents of the RAM in 256. Here's another sort of final example, which is kind of symmetric. Here we do something that looks strange. We do asterisk Q equals 9. Well, asterisk Q stands for the memory location, which is addressed by Q. And Q happens to be 1024. So asterisk Q stands for RAM 1024. And we want to put in it the number 9. So instead of seeing 5, as we see here on the right-hand side, 1024 will contain the value 9. And if we then do Q++, RAM 1 will become 1025. Now you may ask yourself, why am I showing you these two particular pairs of commands? Well, it so happens that these two pairs of commands will be used extensively in what follows. So I wish to once again emphasize that what we saw in this example so far is sort of high-level, or I call it pseudo-assembly code. And in order to actually implement it, you have to take every one of these instructions, pseudo-instructions, and rewrite them in your assembly language. If you use the hack computer, you have to write the code in the hack instruction set. If you use some other computer, you have to write the same code, which is seen here, using the target computer, the target language of your computer. All right, so moving along, here is how we implement the stack abstraction on a real computer. This is the abstraction. We saw it all along. And we see here an example, an arbitrary example in which we take a stack, we push 17, we get a different stack state. And what I want to show you next is how these two states are going to be mapped on physical memory. So here's the host RAM that we are going to use. And we're going to make two important assumptions. First of all, the stack pointer is going to be stored in RAM 0. And the second assumption is that the stack is going to begin in address 256, which looks like an arbitrary choice, but later on you will see that this choice actually makes sense. So with these two assumptions in mind, let us focus on the left-hand side of the slide. And the stack that we saw above, the abstract stack, which is 12 and 5, will be mapped on the RAM beginning in address 256, as we assumed. And therefore, the stack pointer, which always points to the next available location, now contains the number 258. Now, following the push constant 17, if we look at the top, we end up with the abstract stack state on the top right of the slide. And if we look at the bottom now, you will see that within the RAM, the number 17 ended up located in RAM 258, which happened to be the previously available space, and stack pointer has moved one position forward, so now SP contains 259. So that's how we're going to model it on the RAM, and of course we now have to write the assembly commands that will actually make this transformation work for us. So the logic or the implementation of push constant 17 is going to be as follows. At SP equals 17, and the meaning of this is, go to the address that SP points at and put there the number 17, and then increment the address that SP points at so that the stack pointer will move one position forward, because we want it to always point to the next available location in the stack. So the next challenge that we have is to take these two commands and re-express them or translate them into assembly. And we're going to do it using the Hack assembly language. So in Hack, it's going to be as follows. First of all, we want to store the number 17 somewhere. And one way to do it is to say at 7, using the A register as a data register, and then D equals A. So we'll end up having the number 17 stored in the D register. Next, we want to do S stored, and then D equals A. So we'll end up the A register as a data register, and then D equals A. So we'll end up having the number 17 stored in the D register. Next, we want to do asterisk P or asterisk SP equals equals 17, and we do it as I showed you in the pointer manipulation demonstration. We do at SP, A equals M equals D. If you don't understand this logic, go back to the pointer manipulation crash course a few slides back and check it again. So this will accomplish the assignment of the value of D into the topmost stack location. And finally, we have to remember to increment the stack pointer. So for this, we do at SP, M equals M plus 1. Once again, I want to remind you that if you don't understand this code, you have to stop and convince yourself that you understand it. You have to practice it. You have to look back at the program that you wrote in Project Zero and make sure that you understand, this intricate business of indirect accessing, addressing using the A register. Note, if you look at this piece of code, we're using the A register here in two remarkably different ways. In the first two instructions, we use the A register as a data register. We put the number 17 into it, and then we move it into D. Now, the A register has this automatic side effect that it always selects a certain location in the RAM. So when we say, at 17, memory location 17 is going to be selected, but we don't care about it. We don't give it any attention, because all we want is to take the number 17 and move it into D. So who cares if it also selected something in the RAM? We don't care about it. In the next three commands, boy, do we care. In the next three commands, we use the A register as a classical addressing register. We set it up carefully using the pointer, and then we zero in on M, on the RAM location that the A register addresses, and we put the value of D exactly where we want it to be. So this piece of code is, has more to it than meets the eye, and once again, you have to make sure that you understand it before you continue with this module. Now, I would like to observe that there's nothing special about the number 17 in this particular example. And therefore, what we saw here is a general implementation of the generic command push constant I, where I can be any non-negative integer, right? All you have to do is replace 17 with I, and everything will work perfectly well. And that's actually what we do in the next slide. In the next slide, we look at the generic command push constant I, and we see that in order to re-express it in machine language, we have to use the two pseudo commands asterisk sp equals I, followed by sp plus plus. Now, who is going to do this? The VM translator is going to do it. You have to write a program called VM translator, which you'll probably write using Java or Python. This program will receive as input a stream of VM commands, of which push constant I represent one of them. And given this input command, your VM translator is going to re-express it using several assembly commands that basically carry out the semantics which is described on the right-hand side. So on the right-hand side, we have the semantics asterisk sp equals I, followed by sp plus plus, and you have to express this semantics in assembly. And once you know how to express it in assembly, you can write a program that actually does it in a very general sense, for any given push constant I command. All right, so The VM translator is a program that goes from the left to the right, that translates VM code into machine language, and each command like this one naturally is going to generate several assembly commands. All right, so this has been the module in which we began to talk about the VM implementation. So far we talked about implementing one command only, push constant I, and in the next units of this module we'll talk about implementing all the other commands that we discussed before from an abstract perspective. Now we'll talk about how we actually make them work. In the previous unit, we started to talk about the VM implementation, and we went through the implementation of the stack architecture. And in this unit, we'll continue with the implementation of the memory segments. Now, to remind you, we started this journey of the virtual machine with a stack that interacts with some abstract memory space, and then we replaced this abstract space with 8 memory segments whose names are local, argument, this, that, constant, static, pointer, and temp. And the question, of course, is how to implement these memory segments on the host computer. Well, before we get started, let us note that the abstraction of these memory segments is quite uniform. We address any location in any segment using exactly the same syntax: push, pop, segment name, followed by a non-negative integer. So examples include push constant 17, pop local 2, and so on and so forth. So how should we go about implementing these memory segments? Well, we'll do it one step at a time, beginning with local. Now, the local segment is accessed using the uniform syntax that we had all along: push, pop, segment name, index. So here's the local segment in the context of our this simple example of a stack machine. And how do we realize these two data structures on the host RAM? Well, the stack is going to be implemented as we did in previous units. We will start the stack at 256, which is an agreed upon convention, and we use a pointer that we call SP to record the address of the next location, the next available location in the stack. And we decided that SP will be mapped on RAM 0 in the host memory. Now, what about the local segment? Well, the local segment can be placed in principle anywhere we want on the host RAM. We don't care where the local segment is going to be stored, as long as we remember the base address of this block. And as you see here, we've decided to place the base address of the local segment in a pointer called LCL, and we also decided that LCL will refer to RAM 1. So as you see in the example, the local segment happens to begin in this arbitrary address that I made up, 1015, and LCL contains the same address. So notice that indeed we're using two pointers, but we use them in a very different way. The stack pointer points to the next available location in the stack, and LCL points to the base address of the local segment. All right, so here's how we use this implementation when this address of the local segment. All right, so here's how we use this implementation when here's of the local segment. All right, so here's how we use this implementation when we set out to implement commands like pop and push. So here is the same RAM segment that we had before, and SP and LCL are mapped as we had before. And following the pop local 2 command, here's what is going to happen. SP has changed to reflect the pop operation. And we see that the number 5, which used to be the topmost value on the stack, is now located in local 2. Which happens to be 1017. Now, how do I know that local 2 is 1017? Well, that's simple. I take the base address, which is 1015. I know this information, right? It's always stored in LCL. And I add the offset, or the index 2, to it. And by adding up these two values, I get the value of the target address on which I have to store the popped value. Okay, so that's how I can generalize this translation process. I can take the base address and add the offset to it. Another thing which is interesting to note here is that look at address 257, right? It contains the value 5, but notice that this value is out of play. You know, it's kaput, it's dead. It doesn't know it, but it's dead, because the stack pointer now points at 257. So the next push, which will happen probably at some point, is going to kill this number 5, and that's perfectly okay. So it's quite typical when you manage a stack that you have all sorts of garbage along the stack, and yet the pointers indicate exactly which part of the stack are in play and which are kind of game and can be recycled at will. All right, so how can we translate the pop operation? Well, we can do it using the pseudo assembly code that you see here. First of all, we compute the target address, which is LCL plus 2 in this example. We store it in some temporary variable. If we need such a variable. Then we decrement the stack pointer, and we take the value which is stored now under the stack pointer, or the value that the stack pointer points at, and we put it into the address that ADDR points at. So this is the semantics that we want to implement. And how do we implement it in assembly? Well, that's your job to do it. You have everything that is necessary in order to translate such pseudo instructions. Obviously, you will need the heck language, you will need the A command, the C command, and so on. So that's a little sort of riddle that you have to solve. And once you do it, you will know how to always implement pop local I commands. So in general, indeed, you have to observe that there's nothing special about this number 2. I can replace 2 with I, and then everything will work just as well as it did before. Instead of doing LCL plus 2, I will do LCL plus I. So I managed to indeed generalize this translation completely, and I know how to handle pop local I. So here is the generalized translation of pop local I command. What we see on the right-hand side is exactly what we had in the previous slide. And the push local I command is implemented in a very similar way, somewhat symmetric. Okay, so we compute the target address as we did before, and then we carry out a push operation using sort of 2 pseudo instructions. And once again, in order to actually make it happen, your VN translator has to generate the assembly instructions that will realize this pseudocode using the heck language. Now, I would like to realize this pseudocode talk now about hack language. Now, I would like to extend the picture and talk now about these four segments together, the local argument, this and that segments. And it always helps to sort of extend also our perspective and remember or think about where these segments come from or what purpose do they serve in the sort of larger enterprise of what we're doing. Well, think about a typical method in, let's say, in Java, which is operating in runtime. Well, this method typically has local variables. It has argument variables. Typically, it processes some current object, which is also a bundle of so-called member variables, I think. And also, the method may well think about a typical method in segments. And it always helps to sort of extend also our perspective and remember or think about where these segments come from or what purpose do they serve in the sort of larger enterprise of what we're doing. Well, think about a typical method in, let's say, in Java, which is operating in runtime. Well, this method typically has local variables. It has argument variables. Typically, it processes some current object, which is also a bundle of so-called member variables, I think. And also, the method may well process some array that also has entries, which are, data values. So when we translate this logic into the world of the virtual machine, we have to preserve all this semantics. Well, we do this with the local and argument memory segments as well as with two other segments that we call this and that. This segment stores the an argument. When we translate this logic into the world of the virtual machine, we have to preserve all this semantics. Well, we do this with the local and argument memory segments, as well as with two other segments that we call this and that. This segment stores the member variables or the values of the fields of the current object, and the that segment stores the values of the array that the current method may be processing. So basically, we are using these four segments in order to capture this semantics also at the VM level. So how do we implement these four memory segments? Well, first of all, let us remember that abstractly, we use them exactly the same way, right? We do push and pop, segment name, index, and that's it. We don't need anything beyond that. So they are accessed in a uniform fashion. Well, I'm very glad to report that we also implement them in a precisely the same way. In addition to the stack pointer, which is always available, we are now also going to use 4 pointers, which are called LCL, arg, this, and that. And every one of these pointers is going to do exactly what the LCL pointer did in the previous slide. Slides. They are all implemented precisely the same way, and every one of them holds the base address of the respective memory segment that it relates to. And therefore, the implementation of the commands push and pop is also going to be exactly the same. We're going to use the same semantics that we used for the local segment, but instead of saying local, we'll say segment pointer name, where the segment pointer being the corresponding pointer to the memory segment that we are dealing with in the source code, in the VM code. Now, you may well ask yourself a good question here, which is, wait a minute, where exactly on the RAM these segments are going to be located? Well, the answer is, we don't care. Okay, we don't care because they're going to be located somewhere, and all we have to do is remember the base address of these dynamic allocations. Well, later in the course, we'll see that deciding where to put these segments in memory is a very interesting question. And we solve this question using all sorts of clever algorithms, which are going to be part of the operating system and the compiler that together will decide where to map these segments on the host RAM. The next segment that I want to discuss is called constant. And the context of these constants is that when the compiler encounters constants in your program, in your high-level source program, it handles these constants by generating VM commands that include or that use the constant memory segment. So it is going to be re-expressed using operations like push constant something or pop constant something on the stack. So how do we implement these operations? Well, here's the generic push constant I command. And there's no pop constant because it doesn't make any sense to store something in this constant. And the implementation of this constant is trivial because this is a truly virtual segment, right? It doesn't really exist. So whenever we see a push constant I command, we simply generate low-level code that supplies the specified constant. So we do *sp equals the specified constant, and then we advance the stack pointer. So this has been the treatment of the constant segment. Moving along, the next segment that we're going to deal with is the static segment. Now, what's the story of this segment? Where does it come from? Well, the compiler that handles your high-level code may well encounter some static variables. These are the so-called class-level variables that every method in your class sees. So obviously, we have to treat these variables differently than in the way we treat local variables or argument variables and so on. And therefore, we've decided that in the virtual machine abstraction, we will use a dedicated segment called static to represent static variables in the source code. So every operation on a static variable in the source is going to be re-expressed as a push static I or pop static I operation at the VM level. So here is how we're going to implement static variables. Well, we start with some example of VM code in which using static variables comes to play in the context of pop instructions. Now, let us remember what static variables are all about. Unlike local variables and argument variables, which are unique for each VM function, static variables are at a higher level of scoping, and therefore all the VM functions in your program should see the same static variables. And therefore, since we have this functional requirement, it makes sense to store, or actually it's required to store the static variable in some global space that all the code which is generated from these VM functions, will see the same static variables. And so the decision that we decided to undertake is to have the VM translator translate each reference to static I in some VM file foo.vm into the assembly reference foo.i. So foo, the prefix of this label, is the name of the file, and I is the index which is taken from the VM command. Static 5, I equals 5. Static 2, I equals 2. And so if we follow this convention, which will become understood in just a few seconds, then the VM translator is going to translate pop static 5 into, well, first there'll be some code, which I omitted, that carries out a pop from the stack, and the topmost value from the stack is going to go into, I suppose, the D register, the data register, and then we have to put it into our assembly level incarnation of static 5. How do we do it? Well, we generate a label called foo.5, and then we say m equals d. What about the other command? Well, we handle it in exactly the same fashion, only instead of 5, we're going to generate 2. Now, why is this going to actually work out? Well, remember, following assembly, the heck assembler, by convention, is going to map these references onto RAM 16, RAM 17, all the way down to RAM 255. I'm sorry, 255, in case you have so many static variables in your program, which is unlikely. Typically we have just a few static variables in a typical computer program. So what will happen is that these references will end up being mapped to the blue area that you see here on the RAM, and that's exactly what we want. Because you see, this blue area is outside the stack, and all the functions which are running in your program can take a look at this RAM area and see exactly the same thing, the static variables. And so in using this trick here, we basically took advantage of this unique convention in the heck assembly that in the heck assembler of mapping symbolic variables onto the RAM from position 16 onward. And therefore, the entries of your static segment are going to be mapped on RAM 16, RAM 17, and so on in the order in which they appear in your VM code. And therefore, you will have this slightly peculiar situation in which static 5, in this example, will go to RAM 16, static 2 will go to RAM 17, assuming that static 2, that there are no more static variables declared and used in between. So there's no one-to-one. There is a one-to-one mapping, but the order of the indexes, index values is not the same as the order of the RAM entries. It's the order of appearance in the code which determines where each one of these variables will be mapped on the RAM. It's the order of appearance in the code, same as the order of the RAM entries. It's the order of appearance in the code which determines the order of the indexes, index values is not the same as the order of the RAM entries. It's the order of appearance in the code which determines where each one of these variables will be mapped on the RAM. So that's how we implement the static segment. It's a little bit hairy, but it works, and it works quite well. And I'd like to sort of say, make a general observation about this implementation here, and that is that up until this point, up until we discussed static variables, everything that I said in this module was completely platform agnostic. After all, every computer has a RAM, and everything that I said about implementing local argument and so on did not make any assumptions about the underlying platform, aside of the assumption that there's a stack somewhere, which is a very safe underlying platform, did not make any assumptions about the underlying platform, aside of the assumption that there's a stack somewhere, which is a very safe assumption, because once again, we can, every computer has a stack somewhere. And it is only here in the implementation of static variables that we take an exception. And it is only here in the implementation of static variables that we take an exception to this platform independence elegance, and we actually take advantage of something which is unique, was that we take an exception to this platform independence elegance, and we actually take advantage of something which is unique to the Hack assembler. So once again, up until now, everything that I said can be implemented on any computer out there, not necessarily on the Hack platform. And yet, if you want to implement the static segments, you have to find some other tricks to do it if you decide to implement our virtual machine on a computer which is not a Hack machine. All right, moving along, the next segment that we want to discuss is temp. Now, why do we need a temp segment? Well, it so happens that when the compiler generates code, when it translates your JEC program into VM code, it sometimes has to use some temporary variables. So we decided that we're going to allocate an 8-place segment called temp that will contain and serve these variables when needed. All right, so here's how we do it. The push and the pop are uniform, exactly as we had before, and yet temp is going to be a fixed 8-place memory segment, and we decided to allocate or to map this segment on RAM locations 5 to 12. So altogether we have 8 values there, and therefore the translation of push and pop are going to take this base address 5 obviously into account. So it's almost the same as the translations that we had previously, except that the base address is now 5 instead of one of the segment pointers. So that's how we implement the temp segment. The last segment that we have to worry about is called pointer. And the pointer segment is a little bit obscure. And it's obscure because you can't understand really why we need it until you begin to write the compiler, which is something that we'll do down the road in the course. So for now, I'm just going to explain the pointer segment as some sort of almost an arbitrary rule of the game. And given my explanations, you will have all the information in order to actually realize it on the target machine. So first of all, where does this segment come from? Well, it turns out that when the compiler translates a method, it has to remember the base addresses of the this and that segments. These are the segments that represent the current object and the current array that the method may be processing. So we decided to keep the base addresses of this and that in this pointer, segment, which we decided to call pointer. So here are the rules of the game. Pointer is a fixed memory segment. It has only two entries, 0 and 1. And therefore, the only push and pop commands which are applicable here are push and pop pointer 0 and 1, and any other integer is simply invalid in the context of pointer. Now, what do we do with these commands? This was just the syntax of the commands. Well, whenever the VM code tries to access pointer 0, it should result in accessing this. And whenever it wants to access pointer 1, it should result in accessing that. So the implementation should serve service these push and pop commands by supplying this and that. So with this in mind, or with that in mind, as you please, let me say a few words about how we actually do this implementation. So the push pointer 0 command should be implemented as follows. You want to create assembly code that realizes the abstraction *sp equals this, followed by sp++. If the VM command is push pointer 1, you do exactly the same, but you use that instead of this. And the handling of pop pointer is symmetrically similar. Now, I wish to remind you that the assembly code that you see here is pseudocode, and you have to realize this pseudocode using heck assembly. So that's how we handle the pointer segment. Now, I must admit that this segment and the way we use it and realize it may sound somewhat peculiar and strange, but you shouldn't worry about it because it will make perfect sense once we talk about code generation when we set out to write the Jack compiler. For now, let us just strive to create this functionality that I described here. Now, before we end this unit, I'd like to recap and observe what we are doing. So basically, we're implementing the VM language, which consists of arithmetic logical commands, memory access commands, branching commands, and function commands. By now, we've implemented the first two categories of commands, and the remaining two categories are going to be handled in the next module of the course. So before we get to this module, we still have some work to do here. So I'll meet you in the next unit when we talk about the VM emulator.